Hello again, everyone, and thanks for joining us for another particular live webinar. This is Tomek Masternak, and today I'm joined by my colleague and solution architect, Szymon Pobiega, who's going to talk about DDD patterns in distributed systems. Just a quick note before we begin, please use the Q&A feature to ask any questions you may have during today's live webinar, and we will be sure to answer them at the end of the presentation. We will follow up offline to answer all the questions we won't be able to answer during this webinar. We are also going to record the webinar, and everyone who will receive a link to the recording via email. Okay, let's talk about DDD. Szymon, the floor is yours.
Thank you, Tomek. Okay, let's get started. Mandatory slide with my background that we can skip by really quickly. I used to be more active in the domain-driven design community. I'm not that active anymore, unfortunately. Hope to get more done in that community. I used to be involved in event sourcing. And last thing, but not the least, I am an engineer at Particular Software, helping people build distributed systems. And some of you who may have seen my presentations in the past probably expected this guy. It's a typical architect, an old man with beard and gray hair. So usually my presentations start with this guy designing the architecture. This is not the case today. Today we'll have a much more interesting team of architects that I think better reflect the reality of software engineering because we no longer usually have a single architect in the ivory tower. Team members play the architect role. Many team members play the architect role. Sometimes all of them play the architect role at the same time. Sometimes one of the team members take the lead. And also each of those architects or all those people that play the architect role have their personalities and their backgrounds that influence how the architecture is designed. Okay, so let's get started. This lovely team of architects went on to design a system for selling online potions. Potions are very important for ponies because if you are preparing for a major holiday in the Ponyland, you need to stockpile some potions, magical potions. And this e-commerce system is going to help ponies find and purchase the potions they need for a particular holiday. So if you're building an e-commerce system, the first thing that you're probably going to start with is a shopping cart. And this is precisely what the ponies did. And for the shopping cart, the lead architect role happened to be assigned to Pinkie Pie. So Pinkie Pie is our first pony architect that we are meeting today. She's very enthusiastic about stuff, so she quickly jumped on this task and started designing, because that's what architects do, right? So that's the first sketch of the architecture of the system. It's pretty straightforward. The most basic type of architecture, I would say. There is a user interface that runs in the browser, HTTP protocol between the browser and some component on the server side. That is the shopping cart component, and a database that stores the data. This is something we all start with. But that was deemed not enough, because the ponies expected that before the major holidays, there will be much higher traffic on the website. So they wanted to build scalability in, and they heard about message queues, and they heard that message queues help in achieving higher scalability. So they introduced a message queue behind the web server, so that when there is more requests than the shopping cart component can handle, those web requests won't be just plain rejected. They will be queued in that queue, and the shopping cart will update the database. But what happens on the other side of things, how users of that website would know if they manage to put something into the shopping cart or not? Well, the user interface is going to poll the database through the web server. Is that item added? Not yet. Is that item added? Not yet. And that's how the interaction will work. And that was supposed to work, at least on paper. But the user experience team was not really happy because the delay between some user clicking add item to the shopping cart and actually seeing that item in the shopping cart was much too long. So our Pony architects introduced a small change in the system. They added another queue, and the shopping cart component now updates its database and also posts a message to that return queue, and that message gets transferred, gets mapped to a WebSocket package, and that WebSocket packet gets to the UI. So it's much faster now because there is no polling and no polling interval. As soon as the add item to shopping cart message is processed, the user sees a change in the user interface. Okay, that was supposed to be the plan, but here we meet our second Pony architect, Fluttershy. Fluttershy doesn't talk too much because, well, she's shy, but when she does talk, she usually has some very insightful things to share. And in this particular moment, what she started questioning is the queues. So all the ponies gathered together and started thinking about queues. When queues help in a distributed system, and they made a list of things that are required to be there for the queues to be helpful. First, there needs to be higher than capacity load. Yes, that's something that the system is going to experience before major holidays. But that higher than capacity load has to be for a short period of time, like seconds or minutes. Well, that's not what the ponies expected from their e-commerce system. They expected the higher than capacity load to last for a few days before the holidays. So there is something off here. And then the second condition for the queues to be helpful is that further action needs to does not depend on the outcome of the previous action. So let me describe it in this way. When you're submitting an order, you click submit, and then you expect that your order will be processed by the e-commerce site. So you click submit and you go out with a dog, or you just go to sleep and expect your order processed by next morning. But if you are interacting with a shopping cart, that's not the flow. You're adding items to shopping cart, removing them, reviewing the order, clicking here and there. And each action depends on all your previous actions that you did on the website. So queuing your commands to add item to a shopping cart or remove item from a shopping cart doesn't really help you because you still need to wait until that item is put into the queue, picked up from the queue and processed. So queues are not really helpful in that scenario, right? So the ponies had to come back to the drawing board and start over. But this time the lead architect role was taken by Fluttershy. So what she did is she took that basic design with shopping cart and she used a different approach to handling higher than capacity load. She heard about serverless, like Azure Functions and AWS Lambda, and she figured that that would be ideal solution for their problem, because with serverless, you still don't need to pay for the capacity that you're not using, but you can maintain the higher than usual capacity for extended periods of time, like for 3 days in a month, which would not be the case with the, which is the case where queues would not be really helpful. So they decided to use serverless for scale out. And what serverless did is it pushed them into the direction of questioning how much stuff they do while handling a web request. It probably could be seen even before they switched to serverless technologies, but serverless makes it really plain explicit that you should just take the request, do the minimum thing you need to do, and return the response. And that means that there are some asynchronous things that needs to be done while processing order for potions that don't really belong to that request response pattern. So ponies had to introduce some solution for that. And the easiest one that they thought was batch job. Well, these days, if you want to be trendy architect, you don't call it a batch job. You call it a function that is triggered by a cron trigger, but still the concept is the same. You're running some piece of code that is doing some processing on the backend. And that worked for a while. But at some point, ponies realized that it's not going to be the solution for them. They need at some point to break down their system into smaller components, because just pushing more and more stuff into that batch job was making the code less and less readable. And they were worried that they won't be able to build that system on time. So they started introducing components like shipping or billing. And now the question is, how do you cross the gap between the shopping cart and shipping? The user interacts with the system, they add items to the shopping cart, they remove items, and at some point, they click submit to submit the order. And when they submit the order information should go to shipping and billing and other components, and also the shopping cart should be updated to reflect that state. Well, one way to do it is, let's just use HTTP. Nobody gets fired by choosing HTTP as a communication layer for their systems, right? The problem, though, with that approach is that what's happening when you want to submit the order? The user interface sends the HTTP request, and that HTTP request needs to update the state of the shopping cart. Let's say update state of the shopping cart to order submitted, and then fire another HTTP request that goes to shipping component, and that another HTTP request conveys the shipping information and all the items that need to be shipped. And that information needs to be stored in another database. And only then, after those two database updates or inserts are done, we can return the HTTP response to the user interface. Well, you may notice now that it involves updating two separate databases. And without distributed transactions, and we don't have them for web requests, there are going to be partial failures. So either one of these database updates succeeds, or maybe the other, maybe none of them succeeds. There are going to be failure scenarios that will result in customers seeing weird things, like the shopping cart in a state order submitted. So they would think, oh, that's fine, I will get my potions. But shipping would have no information about that particular order because the HTTP request failed at some moment. So they decided that's not going to be a solution in long term. They tried to redesign it, and they did so by breaking down this transaction into two pieces. So first, when the user submits the order, the state of the order is only updated in the shopping cart component. And then there is a batch job that selects the orders in that submitted state and transfers the information about those orders to the shipping component, which stores them in a database. And if that fails, the batch job can always retry passing that information to shipping as many times as needed. So there is failure handling built into that system. And ponies were happy with it, at least at least Pinkie Pie and Fluttershy were quite proud with that. But this is the time where we meet our third pony today. She is Rainbow Dash, and she's known for being a very fast flying pony. And she sometimes pokes holes in the cloud that cause rain or thunder. And she's also known for a thing that many architects are known for. And I speak of experience because I used to be an architect. They just come down from the ivory tower and they leave a drive-by comment about your system, and then they go back up into their ivory towers, and the development team is left with a comment that they have to act on, and they don't know what to do. So here's her comment. So you decided to build a poor ponies queue, right? And the ponies are puzzled. What did she mean? But she's a very smart pony. So all the other ponies started thinking really hard, what's going on here? Maybe something is really off. And after a while, they realized what Rainbow Dash meant. She meant that this system of a batch job and HTTP requests and storing stuff in a shipping database is basically a message queue in disguise, because we are taking stuff from one database to another database, transforming it along the way and going through some sort of API. It could also be seen as a good old replication of a database. But for this purpose, let's treat it as a message queue. At least that was the first thought that Rainbow Dash had, and all the other ponies agreed. So they did to they came back to the drawing board and they replaced that whole system with a nice tidy message queue. And they were very, very happy with that design. And let's see what the code looks like when they actually started writing it down. This is a web method that handles submit order request. It gets the order ID as a parameter. It loads the order from the database. It calls submit method on it, which changes the internal state of that order. And it begins the transaction. And within that transaction, it stores that order in the repository. Then it publishes event submitted event, the order submitted event that notifies the other components of that system that an order has been submitted, and then it commits the transaction. Sounds simple, right? But here's a moment where we meet our next pony, Rarity. Rarity is known for having very close attention to detail, and she usually notices things that other ponies don't see. And this time she looks at the code and says, "Ooh, how are you going to send a message and update the database in a transaction?" What does she mean? Well, take a look at those two lines. So in line 1, we publish an event, and in line 2, we commit the transaction that stores state of our order. And now, depending on the order of those two operations, we might end up with two partial failure scenarios, which are really not going to be liked by the user. So first scenario is a message in that order of things. The order submitted event will get published, but then if line 2 fails, it means that shipping and billing will carry on processing the order, while the order state is not really updated. So for the user, the order appears to be still in the not submitted state. And the user might think, oh, well, never mind, I won't buy those potions. And they can go away and not expect to have a delivery next day. The other situation is if you flip those two lines by trying to fix it, you'll end up in an opposite situation where the user would see a correct state order submitted, but the other components of the system would not know about that order. So there are partial failures in that scenario, and there are two ways of dealing with those partial failures. The way number one is you can have a distributed transaction between your messaging infrastructure, the bus, and your database. Well, you cannot have them any longer unless you're using old technologies like MSMQ. So what's the option two? Option two is to use the same transactional resource for messaging and for database. And sub-option one is let's use a message queue as a database. Well, as you might imagine, message queues are really poor databases. So the only other option is to use a database as a message queue. Well, that might sound weird, but at least we can try or try to imagine it. It can be done with a relational database, can be done with other databases, but let's focus on the relational database scenario. You can imagine a table that has two columns, a sequence number and a payload or a body. And then if you treat that table as a queue, you need a way to receive messages from that queue. And you do it by issuing a destructive select, so-called, which is a select that is wrapped, that is a subquery to a delete. And it works in such a way that you select the oldest row from that table, ordering by sequence number. And with those two table hints, update, log, and read past, you ensure that concurrent selects will select and log different rows. So the concurrent threads won't step into each other's toes. Finally, you delete that row and the output clause tells it to return to the application server. Of course, the row isn't immediately deleted. It will be deleted once the transaction commits. So when we use this pattern, we change the code a little bit. Now we load the order, we begin the transaction, save the data into the database within that transaction, but we also publish a message within the same transaction. And then when we commit that transaction, both save and publish will atomically be sent to the database. That's a huge win because now we are not vulnerable when it comes to those partial failure scenarios. But this is precisely the time when Rainbow Dash flies in again and says, "Ooh, so you did decide to build a poor ponies queue, right?" Well, what does she mean? Well, you can find that on Twitter. Usually, if you ask about building a queue in a database, we will get a lot of comments along the lines of, "Don't do that, it's not going to work," and blah, blah, blah. So ponies, after consulting Twitter, they decided to actually check by themselves. And they picked a 8 vCore SQL Azure instance because it's very standard thing that you can replicate yourself. It costs you $2 per hour. Not a big amount, not a small amount, whatever. And that SQL Azure instance with a decent messaging code can give you 800 messages sent and received per second through a queue in the table. That means that it's almost 3 million messages per hour. Why am I quoting the per hour numbers? Well, you'll see in a second. Almost 3 million messages per hour means that you pay $0.007 per 1,000 messages. Okay. Put it into a context. Azure storage queues, if you use 3 operations for each message, meaning you put a message, then you get a message, and then you delete a message, costs you around 0.0012 per 1,000 messages. That means that SQL-based message queuing is twice cheaper or 50% cheaper than Azure storage queues, which is the cheap way of sending messages in Azure. Well, that's not precisely that, because if you use bigger messages, Azure won't be as efficient in pushing those messages through the table. But what is important here is that it's the same order of magnitude, and that 800 messages per second or 3 million messages per hour is a lot if you're counting your business-related messages, because you can earn a lot of money by pushing that amount of messages per second, even if you get a tiny little profit margin per each transaction. But if that is not enough for you, the pattern that you might be interested in is polyglot messaging, which means that you're using 2 different messaging infrastructures in the same system for different purposes. Let's say one part of the system, like the part that is handling the user interaction here, needs to have strong consistency guarantees, and you're using a SQL server as a messaging queue. And then there is another part of the system for which the most important factor is scalability, and then you use other storage queues in that part. And in between them, you put something like a transport bridge. Such transport bridge can be built with a service bus, for example, if you just use transports directly. And to remind you, and service bus transports are public API of particular platform, so you can just use transport outside of the endpoint if you don't need serialization and pipeline and that kind of stuff to just move messages from one queue to the other. Coming back to our story, this is the architecture that the ponies were working with. And I think this is appropriate time to meet our next pony and last for today, or second to last. Actually, she's Twilight Sparkle, and she is a Martin Fowler type of pony, if you know what I mean. She sees patterns where others fail to see any relationship, and she looks at things, multiple things, compares those things, and can see what are the relations. So she looks at that diagram and says, there is something into it. And this is what she means by it. She noticed that there is a pattern that is repeated in that system all over again, over and over again. There is a synchronous part of a business process and an asynchronous part of the business process. And the synchronous part is when the user interacts with that system, for example, through the shopping cart. So the user adds things to the shopping cart, removes things from the shopping cart, and makes many decisions. But at some point, the user arrives to a conclusion. Either they are submitting that set of data that they built, or they are abandoning it. Hopefully, they submit it. And when they submit that set of data gets transmitted as a message to the async part of the system. And the async part of the system consists of components that communicate through queues, message queues, And the asynchronous part of the system is where the majority of the business process is happening, but the user is not waiting for that part to complete. Well, they would rather have their goods delivered by tomorrow than in 3 days, but the user doesn't care if the business process completes in 5 seconds or 10 seconds or maybe 30 seconds or 5 milliseconds. That pattern is not applicable to any system. There are systems in which the whole business process needs to be carried out in certain within certain time constraints. But in most e-commerce systems, there is a clear distinction between the synchronous part and the asynchronous part. And usually the async part is much more complex and bigger, but has no hard time constraints, while the sync part is shorter, much more user interactive, and it's much better done in sync. Okay, so let's try to focus now on that async part, and that will be preparing shipment and billing the customer. And for this part, the ponies decided to start to actually reread the domain-driven design book by Eric Evans, because they expected a lot of complexity being in this part of the system, and they wanted really to to design that part of the system well, because they thought that that's their core domain. And one of the things that they found in that blue book is this sentence: aggregates and entities encapsulate behavior and data. There is a lot of knowledge packed into such a small sentence. And the lead architect here is Rarity, the pony that has the attention to detail that is unmatched. So Rarity took the blue book and tried to implement the concept called application service or application layer. This is a concept in domain-driven design that was meant to reflect a use case in the original book. So a use case is confirm payment. And that use case takes an order ID, it loads the order from the repository, it calls a method on the aggregate, order is the aggregate, and then saves the changes to the database that happened while calling or while executing the confirm payment method. And this is the way we used to build domain-driven design systems 10, 15 years ago, as a collection of use cases that were sort of independent. And the user would select somehow select the aggregate that they are operating on and invoke a use case by passing arguments. Where was the business process there, you may ask? The business process was in the heads of the users. The users would have to know, okay, now I confirm the payment, then I prepare shipment, then I do this or that. That was the way we used to build systems back then, and those systems were usually monolithic. This is not the case anymore. We're living in times where we build distributed business processes. And what is that distributed business process? It's a business process that is automated in software. So it's not the user who clicks here and there and processes payments and prepares shipments. We expect from the systems that we build, software systems that we build, that the process will be carried out automatically, and users will only get notified, or operators of the system will only get notified when there is something that the system cannot handle by itself. That's the system part. The distributed part means that the process is distributed among multiple components that interact. So the shopping cart component stores some information in its database and publishes an event or sends a message to a message queue. And that message is picked up by a shipping component or a billing component, or name that component. And that other component modifies the state in its own database and sends another message. So the process flows. It's distributed because it uses different multiple databases and multiple processes that communicate. If you zoom in into that process or a single chain of that process, for example, shipping, you'll see our component that runs the code. There is a database and a message queue on the left and a message queue or topic on the right. So a message comes in, a message goes out, or messages go out multiple, and then there is some state change in the database. Now let's try to focus on what those messages really are, because messages come in different shapes and sizes. but you can generally categorize messages into two broad groups. Well, there are certain different archetypes of messages, but we'll focus on two groups: events and commands. So how do we decide if a message that drives particular business process should be a command or an event? Well, you may ask Rainbow Dash. She has a say for, like, she has an opinion about any subject, including events and commands, and she says, let's just use events. Why? Because I, Rainbow Dash, say so. How would that business process look like if Rainbow Dash was implementing it? Let's focus on the same part of the process, confirming the payment. So now our application layer, quote unquote, is not just a method, it's a message handler. It handles events of type order accepted, and the message is passed to that method, and we load the order as previously, then we confirm the payment, and next thing is we published order confirmed, because the next part of the process will be handled automatically, not by the user selecting something. So we need to drive that business process by publishing another event, order confirmed. Now, what you may notice here is one strange thing. We handle a message of type order accepted, an event, but we call method method confirm payment on the aggregate. Like, where is that mapping? Why order accepted and confirm payment? There is no place apart from that comment in line 8 and 9 where that mapping is. The business process definition is implicit here and only available in the comment if somebody cared to comment. So when an order is accepted, confirm payment, that's implicit part of that code. But then we meet our friend Pinkie Pie again, and she also has an opinion about everything. So no, let's just use commands. Here's Pinkie Pie implementing the same piece of software. Now the confirm payment handler handles a command of type confirm payment, not an event, a command. What happens here is, well, as usual, we load the order from the repository, we call confirm payment, and then we send another command called schedule shipment. So that's another aggregate, shipment aggregate, can start scheduling shipment of goods. But you notice another thing again here. There is an implicit business process defined here. We call confirm payment method on the aggregate, but then we publish we send a schedule shipment command. What's the relationship between confirming payment and scheduling shipment? Only the comment in line 9 and 10 tells us that when a payment is confirmed, schedule shipment. So the business process is implicit in that code. And the question is, should we follow Rainbow Dash and use events? Should we follow Pinkie Pie and send commands? Maybe we should do mixed. Maybe we should allow each architect / developer to choose their own way of thinking and have a mixture. We don't know. But there is one more problem in that code that only Rarity could notice. So that looks great if you don't have any conditional logic in your business processes, but frequently you do. And frequently when you call a method on an aggregate, the aggregate can react in multiple possible ways. The aggregates, as you recall, the purpose of them is to encapsulate the complexity of the business logic and to guard the domain invariants. There might be times where you send a message to aggregate or call a method on an aggregate, and the aggregate refuses to carry out that command because by doing so, it would invalidate some of the invariants the aggregate protects. So how does your app service know what messages to send? If that confirm payment method might result in success or failure, we need to add a code like this. After, let's say we're following Pinkie Pie command-driven way. If the order is confirmed, then we send a prepare shipment command. If it has not been confirmed, we send cancel shipment. That looks okay, but not for Rarity. She's really devastated because we just ruined her encapsulation, and her aggregates were supposed to guard their data and not let out any information. Thankfully, Pinkie Pie found a solution in a 12-year-old blog post by my boss, Udida Han. about domain events. I tried to rephrase the code that Udi posted 12 years ago in a more modern way, and it goes something like this. We load the order from a database, then we create some sort of in-memory lightweight event broker kind of thing, in which we can subscribe to events. So we subscribe to payment confirmed event, and if that happens, we send prepare shipment command. If there is a payment refused event, we cancel shipment. But where those events come from, you might ask. So we pass this lightweight in-memory event broker thingy to the confirm payment method. And the confirm payment method, that's the part of the aggregate, says, oh, if it's success, if I successfully manage to confirm the payment, then I publish this. Otherwise, I publish payment refused. And when I publish this from the aggregate point of view, my callback registered in the layer above gets called, and I send the prepare shipment method. The big advantage of that way of structuring the code is that the aggregate can have no public properties. The application layer or message handler layer doesn't have to query the order aggregate if the payment has been confirmed successfully. It just passes the event subscriptions, and the aggregate will call one of those callbacks by publishing one of these events. So encapsulation is preserved. And the other benefit of it is we have our business process expressed in more than comments, because we see in line 3 and line 6 clearly the mapping between payment confirmed event and prepare shipment commands. The business process is, well, it's not on its own. It's not coded in a specific separate artifact in code, but at least it's more explicit than in a comment. So thanks, Udi, that can work, but Twilight Sparkle has a better idea, or she thinks she has a better idea. She looks at an aggregate, and she really thinks, and other ponies agree, that aggregates are well suited for processing commands and publishing events. She really got that idea from that domain events blog post, because aggregate can change its state, but can also reject to process a command. Aggregate can look at the command and say, no, that command is going to validate my invariant, so I'll just reject it. But aggregate can publish an event nevertheless. It can publish that something or something was prevented that didn't happen. So that's fine. But the problem is, how do you make a business process out of a thing that takes a command and generates events? You cannot chain them together because they are incompatible. You cannot put one aggregate after the other because aggregates expects commands, and the previous aggregate just outputs events. The missing link here that Twilight Sparkle figured out is the Saga, or otherwise called Process Manager, but I insist on calling this thing Saga because it's more specific to messaging. A Saga is a message-driven process manager. And that process manager reacts on events published by aggregates and generates commands for another aggregate, or the same aggregate, or some different aggregate. And the other idea that Twilight Sparkle had connected to this one is she recalled reading Pat Halland blog posts or article about messaging. And the line that she remembered from that article by Pat Halland is, messages are addressed to entities. And when she recalled that, something clicked. And this is the design that she spiked and showed to other ponies. In her design, a payment is an aggregate, but it's also a message handler. So there is no special application service layer or message handler layer that needs to take care of the aggregates or do the transformation. The aggregates themselves are handling messages. So this time, payment aggregate gets the confirm payment command, and assuming it is the happy path, it marks the confirmed flag as true, but also publishes an event payment confirmed. And that event goes to an order process, which is a Saga, the thing that manages the processes, and also a message handler. In this example, well, it's because it's a Saga, it's an event handler. So it gets the payment confirm event, it modifies its internal process state. So the Saga encapsulates not the business entity state, but the business process state. So in this example, payment confirmed sets to true. It inspects some other piece of its state, like address checked. And if it decides that certain criteria are fulfilled, in this example, payment is confirmed and the address is checked, it can send a command to another aggregate, shipment aggregate, to prepare the shipment. And that aggregate is also a message handler of a command, because aggregates handle commands. It does its business logic, and then it publishes shipment prepared, which can be subscribed by the same Saga, the order Saga, or yet another Saga, depending on the nitty-gritty details of the business process. We can see here, we can clearly spot that there is some duality and commonality between Sagas and aggregates if they are expressed in that way. Both have some state, they encapsulate state. The aggregates encapsulate business entity state, the Saga encapsulates the process state, and both receive and generate messages. So we can call them message-driven state machines, because that's what they are. And that's a pattern that is very useful in building distributed systems. When you think about this pattern, quickly you might realize that everything that you see looks like a message-driven state machine. That would be too easy for Twilight Sparkle to convince the other ponies. Fortunately, there is Fluttershy with her attention to detail. So what she spotted is, well, that can work. That looks good. But what happens if you get a duplicate message? Of course, Twilight has an answer to everything: the Outbox. What is the Outbox, for those of you who haven't used that pattern in your systems? The Outbox is something that prevents invoking a piece of business logic multiple times when that piece of business logic is driven by messages. Let me show you quickly how it works. Suppose we are getting a message, and what do we do? First, we try to load the Outbox record. What that is, you will see in a moment. Because that's the first time we see that message, there is no Outbox record for it. So it's null. So we open a transaction and process that message, be it event or command or whatever. And the result is that we update the database within the transaction, so the changes to the database are not yet committed. But we also generate an Outbox record, and that record contains the messages that are going to be sent out as a result of that processing. And then we store that Outbox record as part of the same transaction. So if line 7 succeeds, both the changes to our business data and the messages that are going to be sent out are committed to the database. If line 7 fails, then nothing really happens. Suppose line 7 succeeds, and we go to line 9, we check if the record is dispatched. We don't know yet what dispatched means, so it's not dispatched. We dispatch the messages from the Outbox record. That means that we push those messages to the underlying queues and topics, the messaging infrastructure, and those messages are delivered to the downstream systems or components. Then we want to mark that record as dispatched, meaning that we send those messages. But let's suppose we're failed here. What happens? Well, nothing is lost, because in line 7, we committed the transaction and data is safe in the database, both messages and our state change. And moreover, the message that we were processing goes back to the queue, because we are using durable queues. So we are going to pick that message again and retry processing it. But this time, the Outbox record is already in the database, so it's not null. We are not invoking our business logic again. So we prevented duplicate message processing here. Is it marked as dispatched? No, because we failed previously in line 12. So we dispatch the messages again. And you may ask here, oh, well, now we are generating duplicates, right? Because we are sending the same messages again. But because those are the very same messages with the same message ID and same message payload, the Outbox components in all the other downstream services will catch those duplicates and will prevent duplicate processing. Now we are going to mark those messages are dispatched, and this time we succeeded, yay. But before actually committing the message received transaction, we fail. Well, message goes back to the queue, we pick it up again, retrying, we check the Outbox record, it's there, and it's marked as dispatched, so we just continue, and we ignore that message as a duplicate. Works really well. but you can count on Rainbow Dash trying to question your design, right? So good for you, but my database has no transaction. And you might think, well, why would you have a database if it doesn't have transaction? Well, there actually are databases that don't have transaction and have valid use cases, and many of them, and you can encounter them in modern systems. The major example being, if you want your database to be really scalable, you might trade off transactions. It's not like you should trade off transactions, but you might if you are building a key value store, for example, that is supposed to handle millions of transactions per second, millions of updates per second, you might not build transactions into it, transactions between multiple keys, that is. But still, you can use the Outbox pattern. There are certain modifications that you need to apply, but you can define the Outbox as part of your entity, as a, for example, ordered dictionary of string and messages. And then when you are storing the Outbox, it just means you're updating your entity in a database. Well, updating your entity in memory before storing it in the database. And that means you are assigning the list of messages generated to the ID of incoming message. And then because you don't want to use all the space in the world, you want to check if this particular Outbox is not too long. If it is too long, you just truncate it. And then when you're marking it as dispatched, it's just as simple as assigning null to that ID in our dictionary so that we don't store the outgoing messages anymore. We don't need them. We just retain the fact that we processed the message. And, well, you might expect, she comes again and says, well, actually, I wasn't right. My database has some transactions. What does it mean, some transactions? Well, there are popular databases these days which fortunately have multi-entity transactions, but those transactions are limited. And a good example is Cosmos DB, which now has transactions, but those transactions are limited to a single logical partition. But there is a very easy way to adopt that Outbox pattern to those databases too. All we need to do is we need to figure out before processing a message which partition that message is going to. And that might be tricky in a general case, but you know what? If we are treating our entities or our aggregates and sagas as targets of messages, we can easily use a partition strategy that assigns each aggregate or saga a different logical partition. And by doing so, we can use the Outbox pattern very successfully. And the result is each logical partition contains either a saga or an aggregate plus the Outbox associated with that message-driven state machine. And with that design, finally agreed upon by all the ponies, they were able to launch the product and achieve great success by selling lots and lots of potions. And with success comes, the price, and the price is you need to keep up with the competition, because when the competition sees that you are succeeding, they want to replicate your business model. And in order to keep up, you need to make your system more complex, usually. Well, not in all cases, but sometimes the solution that the enterprises do is start doing different lines of business. Like you were successful as a taxi company or something like that. And you figure out, well, let's try to do the same in the food delivery space, not pointing to any company at all in particular. Here's the blueprint of the architecture as it was at this point in time. There was a UI running in the browser, the shell, meaning that part of the system that synchronously interacts with the UI and the user, and then the asynchronous core, right? That's our blueprint. But as you can see, you cannot scale the complexity here. You cannot add more components here because there's no space in my slide. So what we need to do is that flip at 90 degrees, and now we have space. So we can make our boxes larger and fit more components into them, more sagas, more aggregates, more components that deal with the user interface, right? But fortunately, there is Fluttershy to warn us about something. what she sees is layer architectures, and she has some experience with dealing with layered or multi-tier architectures back 10 years ago, and she remembers it's not going to end up well. So she says, well, layered architectures quickly get messy, you know, and we know about it, and ponies knew about it. So they didn't try to make those layers wider and pack more stuff into it. The strategy that they wanted to employ is to build more vertical slices, and each business unit, each product, you name it, had a different slice, and those slices, well, they need to be integrated in the user experience layer, because you don't want your user to know that you have different business units in your company, and that potions, for example, are handled in a different component than let's say magical scrolls. So you need some sort of integration there, and web components can help you a lot. And then you need some sort of integration at the bottom in the core of your system. And that can be handled by publishing an event. So an aggregate publishes an event, and then there is a Saga in a different slice of the system that subscribes to that event. So event-driven integration in the core of the system, and some web components integration, JavaScript integration in the top. And with that, I'm almost done with my presentation. I would like to invite you to read a blog that Tomek and I have, and that blog mainly focuses on making the business distributed systems reliable. So the Outbox part, but also we blog about different stuff related to distributed systems. And I also would like to invite you to the workshop that Tomek and I are going to have as part of NDC Workshops initiative. It's going to happen on March 11-12, and it would be about building reliable event-driven microservices. So more or less the same topic as today's talk, but more focused on the reliability part of that. And with that, let me try to recap what we said today, because we're running out of time. First, queues are not a silver bullet, especially for the interactive part of the system. Queues might actually do more harm than benefit. Second thing, SQL Server used as a message queue can get you a lot, but if that's not enough for you, Polyglot messaging is the way to go. And in many systems in the business or e-commerce area, synchronous asynchronous boundary can help you structure your system in a better way. And that's one of the patterns. And then a Blue Book, I highly recommend the Blue Book. If you don't have time to read it, just that sentence gives you a lot of knowledge that is in that book. Aggregates and entities encapsulate behavior and data. The Blue Book probably is not enough these days, because the content is only slightly outdated, because today we deal with distributed business processes, which require, well, not require, but are quite well handled by sending messages to entities, meaning aggregates or Sagas. And that's thanks to Pat Halland's white paper. And we call them message-driven state machines. And we want to protect them usually from having duplicate messages by introducing the Outbox. Last but not least, if you want to scale that system when it comes to complexity and allow more teams to work on that system, vertical slices are the way to go. And with that, I'd like to thank you. Here's a bunch of links, and I'd like to take some time for questions.
Thank you very much, Szymon. We already have a couple of questions. By the way, if we can't get to the question that you asked, don't worry, we will follow up offline with the answers. So let's start with a question about serverless. And the question is, what is your personal opinion on serverless programming, and where would you implement domain layer, aggregate, business logic, etc. in a serverless environment where it seems that every function is a separate, but with a shared state?
Okay, so I think I sort of addressed at least partially this question during the presentation. Serverless, what I like about serverless, it really pushes you toward making the code that handles the request as short as possible and as focused as possible, which is good. And here in the example of this system, that meant that the user interactive part of the system is really interactive and handles requests really fast. And then when you're dealing with aggregates and Sagas on the asynchronous side of things, serverless can also be useful, but this time I would recommend using serverless based on message queues, which can be done both in AWS and in Azure. And with that approach, the function is driven by messages coming into the queue. And for example, and Service Bus supports Sagas on top of this serverless technologies. So if you are used to using Service Bus for Sagas and aggregates, you can do it with serverless technologies and benefit from the billing model that allows you to not pay for the capacity that you are not using.
Thank you, Szymon. The next question was asked by Oliver, and Oliver is asking, how do you keep track of how your application works after you implement a lot of features? How to make it clear where the message comes from and where it's going in your code base, how to manage that aspect of your application?
Okay, that's a really good question, because distributed systems are, well, they have some good advantages, but one of the weak points traditionally was monitoring those distributed systems and making sure they work as they are supposed to do. What I can recommend is for in-service, but specifically the part of the platform tools like Service Control and Service Insight allow you to process all messages from your system, audit them, and visualize them. That's really useful if you want to see what Sagas are doing and generally what components are sending to each other. And then there is a second thing that is not only as in service bus specific. There is this specification called open tracing, if I remember correctly, or I might be mistaken. Anyway, the idea is that with every request, you're passing the trace ID, and then if you're passing those trace IDs from message to message, from HTTP request to HTTP request, then you can build a graph of what really happened in your system, because you have that information embedded in all the calls, and it can extend from from the left to the, well, from the very beginning of the interaction, from the user clicking a button to a database. And for example, Microsoft technologies in Azure supports those tracing standards, and you can figure out the whole interaction from the user clicking the button to Cosmos DB throwing an exception. And I know Jimmy Bogart has an open source project that brings support to those tracing technologies to n-service bus.
Thank you, Szymon. We are almost on, or we are actually over time, but I think that we can answer one more question. And that question asks about chattiness between the services. And do you have any advice about making sure that the amount of that data that passes between the endpoints is minimized? Do you have any advice on that, Szymon?
So what we usually advocate is to not send data between messages. We have a blog post published that has there is a blog post that I can link somewhere. It's called "Put Your Events on a Diet," and basically the idea is that the chattiness, if the service boundaries are correct, there is very little chattiness between those services because the data is not passed between them. That is built on the idea that the service decomposition of the system is based on the data and how data is used, not how the teams are structured. And that's, in my opinion, one of the biggest challenges in current way people build software systems. the services are sort of designed in such a way, like they are designed around teams of two pizzas, for example, and not around the data that they use. So as a result, all the services have the same size because the teams have the same size, and all the services need the same data, so they need to send data between each other. Whereas I believe the correct approach is to actually structure the services based on what pieces of information are used together and updated transactionally. And if you structure the system in such a way and then have your services be vertical from the user interface all the way down to the database, you'll probably end up with much less data passing. And the only data transfer that you will probably end up in such a system is passing the data into some sort of reporting solution, a data warehouse of some sort. But that's usually handled by data transformation techniques or ETL techniques and not by messaging. So my general advice is to look at passing information or passing data through messaging as a kind of smell in the code that might suggest the service boundaries are wrong.
Thank you, Szymon. And that is the last question that we have time to answer today. One additional thing that I wanted to mention is that there are a bunch of events that are happening in February and in March. So make sure to go to particular.net/events. One thing that I wanted to highlight in addition to what Szymon already mentioned is the next webinar, which is going to be about Azure Functions in Practice, which is delivered by Adam Jones. So if you're into Azure and serverless, make sure to register. And I think that it's all that we have for today. On behalf of Szymon, this is Tomek saying goodbye for now and see you on the next particular live webinar.